Glass is everywhere, but almost no one truly sees it. It separates us from the outside world, yet allows us to look through it. It protects us, yet remains fragile. We trust glass with our homes, our vehicles, our phones, our cities, but very few people ever stop to ask a simple question. Where does glass actually come from? Not factories, not machines, but for all of that, the real answer is far more surprising. Glass begins as sand. The paradox of GLA-SAT. First glance, glass seems modern, clean, artificial, almost futuristic. Yet glass is older than civilization itself. Natural glass formed millions of years ago when lightning struck sand, or when volcanic lava cooled too quickly. Humans did not invent glass. They discovered it, and then they spent thousands of years trying to control it. Why? Glass is not what UTHIN most. People believe glass is a solid. It is not. Scientifically, glass is an amorphous material, a structure that exists between states. It behaves like a solid. It is technically a frozen liquid. This strange nature is what makes glass possible, and also what makes it extremely difficult to manufacture. Too hot, and it flows uncontrollably. Too cold, and it shatters. Glass demands precision. Why sand? Not all sand can become glass. Beach sand is too impure. Desert sand is too rounded. Glass. Factories require high purity, silica, sand. Sand composed almost entirely of silicon dioxide. This sand is formed over millions of years as rocks slowly erode into microscopic crystals. Each grain carries geological history. The true fondatio in silicon dioxide is the backbone of glass. When heated to extreme temperatures, its rigid molecular structure breaks apart and rearranges itself. But pure silica melts at temperatures that are too high for industrial control. So humans had to cheat nature. The first modification. Soda ash, to lower the melting point. Manufacturers add soda ash. Soda ash changes the chemistry of silica, making it meltable at controllable temperatures. But there is a cost. Soda ash makes glass weaker and more vulnerable to water. So another ingredient is required. Limestone. The stabilized limestone is added to strengthen the glass and make it durable. This three-part balance, silica, soda ash, and limestone, is the foundation of modern glass. Change the ratios, and you change everything. Recycled glass. The silent, modern glass production relies heavily on recycled glass. Known as cullet, cullet melts faster, uses less energy, and improves consistency. In many factories, recycled glass makes up over 30 to 60% of the raw material. Glass is one of the few materials that can be recycled endlessly without losing quality. From earth to iron, before sand reaches a factory, it is mine-washed, filtered, and tested. Even microscopic iron particles can permanently tint glass green or brown. That is why raw material quality is monitored obsessively. Glass has no forgiveness. The beginning of glass making was manual and dangerous. Today, human hands rarely touch the process. Sensors measure weight, humidity, and composition down to fractions of a gram. Computers calculate exact batch formulas thousands of times per second. This is no longer craftsmanship. This is controlled physics. The furnace, a man-made SUN. At the heart of every glass factory is a furnace. These furnaces operate at 1,600 to 1,700 degrees Celsius. Hotter than lava, hotter than most metals can survive. Once started, they are rarely shut down. Some furnaces operate continuously for over 25 years. Stopping them risks total destruction. Entering the point of no reset or as raw materials enter the furnace. There is no going back. Sand loses its identity. Its structure collapses. Its memory disappears. What emerges is molten glass, a glowing, flowing substance that behaves like a living thing. Why bubbles are the ENEMY inside the molten glass? Air bubbles rise slowly to the surface. If even a single bubble survives, the final product may fail. Time and heat work together to purge these imperfections. Gravity becomes a tool. The beauty of molten molten glass glows in shades of orange, yellow, and white. It moves slowly, almost hypnotically. This is the most dangerous stage of production, and also the most mesmerizing. Factories are built around this moment. Floating glass on liquid MAF4 flat glass. Manufacturers use the float process. Molten glass is poured onto molten tin. Glass floats naturally. Its surface becomes perfectly smooth. Thickness is controlled by speed and gravity alone. No human touch. Control without CONT. The C-trollers never touch the glass surface. Air pressure and timing guide it forward. The glass cools just enough to hold its shape before entering the annealing phase. The slow art of EONG cooling glass. 2. Quickly creates internal stress. This stress is invisible but deadly. Annealing ovens cool glass slowly, sometimes over several hours. This process determines whether glass will survive transportation or shatter without warning. Lasers scan every millimeter of glass. Cameras detect flaws the human eye cannot see. Any imperfection means rejection. Rejected, glass is crushed and sent back to the furnace. Nothing is wasted. The silent DI sure beauty unfinished. Glass travels worldwide. It becomes skyscraper windows, car windshields, solar panels, smartphone screens, and laboratory equipment. Most people never think about its origin, but every piece started as sand. Glass is not just a material, it is the result of controlled chaos, extreme heat, and human patience. And this is only the beginning. Because next, we will explore how glass is shaped into bottles, screens, and precision instruments, where milliseconds decide success or failure.
By the time sand becomes molten glass, it has already passed the point of no return. But melting is only the beginning. Because molten glass is useless, unless it can be controlled, shaped, and stabilized. And controlling something that burns hotter than lava is one of the most difficult challenges industrial engineering has ever faced. The problem with liquid glass: molten glass is not like water. It does not splash. It does not flow freely. It moves slowly, heavily, like thick honey made of fire. Its viscosity changes with even the smallest temperature shift. A difference of just a few degrees can determine whether glass stretches smoothly or collapses into unusable waste. This is why glass factories are built around precision, not strength. Temperature is law. Inside a glass plant, temperature is not a guideline. It is law. Sensors constantly monitor heat levels at hundreds of points. Algorithms adjust burners, airflow, and fuel in real time. There is no pause button, no reset. The process moves forward continuously, whether the glass is ready or not. The birth of form. Once molten glass leaves the furnace, it must be shaped immediately. Delay is failure. Factories use different forming methods, depending on the final product. Flat glass, containers, fibers, optical glass, and specialty components all require completely different approaches. The float glass revolution, deep dive. Before the 1950s, flat glass was imperfect. Surfaces were uneven. Distortions were common. Polishing was expensive. Then came the float glass process, a method so effective that it is still used almost unchanged today. How float glass really works. Molten glass flows gently onto a bath of molten tin. Tin is chosen for one reason: it is denser than glass and does not mix with it. The glass floats perfectly. Gravity pulls it flat. Surface tension smooths it naturally. No grinding, no polishing. Nature finishes the surface better than any machine ever could. Controlling thickness. Thickness is controlled by speed. The faster the glass moves, the thinner it becomes. The slower it moves, the thicker it grows. Edges are guided by rollers that never touch the visible surface. Everything happens without contact. Annealing, the most ignored step. After shaping, glass looks finished, but it is not. At this stage, glass is still under internal stress. If it cools unevenly, it may explode days later, for no visible reason. This is why annealing exists. What is annealing? Annealing is controlled cooling. Glass enters a long temperature-controlled tunnel, called a layer. Inside, heat is reduced, slowly and evenly. This process can take minutes, hours, or even days, depending on thickness and type. Annealing does not change appearance. It changes survival. When annealing fails, poorly annealed glass is dangerous. It can shatter spontaneously. It can fracture without impact. It can fail under minor stress. Many historical glass failures were not design problems. They were cooling mistakes. Cutting glass without breaking it. After annealing, glass must be cut. But cutting glass does not mean sawing. Glass is scored, not cut. A microscopic scratch is introduced along a precise line. Stress concentrates along this line, and the glass breaks cleanly. This technique has existed for centuries, but modern machines execute it with millimeter precision, at industrial speeds. Edge finishing. Raw glass edges are sharp, extremely sharp. Edges are ground, polished, or sealed, depending on application. Architectural glass requires smooth, safe edges. Industrial glass may leave edges unfinished, to be hidden inside assemblies. Every detail matters. Making glass stronger, tempering. Annealed glass is strong, but sometimes, strong is not enough. This is where tempered glass comes in. How tempering works. Glass is reheated, and then cooled rapidly using air jets. The surface cools faster than the core. This creates compressive stress on the outside, and tensile stress inside. The result? Glass that is up to 5 times stronger than untreated glass. Why tempered glass shatters? When tempered glass fails, it breaks into small, blunt fragments instead of sharp shards. This is not a flaw. It is a safety feature. Tempered glass sacrifices itself to protect human life. Laminated glass, controlled failure. Some glass must not shatter at all. Windshields, security glass, bullet-resistant panels. This is laminated glass. The layered approach. 2 or more sheets of glass are bonded with a plastic interlayer. When the glass breaks, the interlayer holds fragments together. The glass cracks, but stays in place. Failure becomes controlled. Glass for bottles and containers. Container glass uses a different path. Molten glass is cut into precise portions, called gobs. Each gob is timed perfectly. Too hot, it deforms. Too cool, it cracks. Gobs drop into molds and are shaped using air pressure. All of TH. This happens in seconds. Speed at an inhuman scale. Modern container lines produce thousands of bottles per hour. Machines operate faster than human reaction time. Any mistake means mass rejection. This is why automation dominates. Coloring glass on purpose. Not all glass is clear. Color is controlled chemistry. Iron creates green tones. Cobalt creates blue. Selenium removes unwanted color. Tiny changes create massive visual effects. Color consistency is one of the hardest challenges in glassmaking. The role of defects. Glass defects are microscopic. Bubbles, stones, striations, distortions. Some defects are cosmetic. Others are structural. Inspection systems use cameras, lasers, and AI to identify problems humans cannot see. Glass has zero tolerance. Why most glass never reaches you? A surprising amount of glass never leaves the factory. Rejected glass is crushed and recycled immediately. This is not failure. It is efficiency. Glass waste becomes raw material again. Glass and energy. Glassmaking is energy intensive. Furnaces consume massive power. This is why factories optimize fuel use, recycle heat, and use cullet aggressively. Sustainability is not optional. It is economic survival. Glass is always watching you. Every stage is monitored. Temperature, pressure, flow rate, composition. If anything drifts outside tolerance, alarms trigger instantly. Glass does not wait for corrections.